Good morning, Year 10, and today we're going to be looking at the magnetic fields of electric currents. And we're going to divide this into two parts. So although in the book it's all on one double-page spread, we felt that there was a lot of content for you to be able to learn on this, and we've divided the lesson into two. So today we're going to be looking at identifying the pattern of the magnetic field around the straight wire and carrying current, know how the strength and direction of the field varies with the position of the. So, as I said, we've divided this lesson into two. You can find the material on page 160, 161. I've also added some bite-sized clips at the bottom because I just thought that they would be useful for you guys. And there are also a couple of links to these YouTube videos that were referred to within this presentation. So, can you put questions 1 to 5 in the margin? And you might need to leave a little bit of space because there's a couple of diagrams. I want you to pause the slide now and have a go at doing these 5 activities. Right, so number 1, sketch and label the magnetic field around a bar. So you should have drawn your bar magnet, a nice long oblong rectangle, and with the north and south labelled with clear arrows moving from the north to the south. What does the ammeter measure in an electrical circuit? It measures current. Does the conventional current flow from positive to negative or negative to positive? It always flows from positive to negative. And how is the voltage measured in a circuit? In parallel. Some of you may put by a voltmeter, and I'll allow that. And then applying your knowledge, magnetism can be induced in magnetic materials. What useful purpose may that serve? And producing a magnet can always be switched on and off and can be used in industry. Electromagnets can be created using electric current, which creates a very strong magnet. Applications for electromagnets include sorting metal in scrapyards, MRI scanners, and hard disk drives for computers. So let's look at our magnetic field around a wire. So what we've got here is a wire up here, and we can see that around my wire I have these lines of force that are what we call concentric circles. So those circles that look like ripples, as if you threw a stone into a pool or a pond. So the electric current passes along the wire and the magnetic field is set up. And when the current is switched on, there is a magnetic field, and when there is current is switched off, the magnetic field is also then disappears. If we were doing this in class, we would be putting this piece of wire through a piece of paper and using a plotting compass to show those concentric circles. If you have a thick enough piece of wire and somebody holding the fuses up, you can do it with iron filings. I wouldn't recommend doing it at home, guys. You get told off by the caretakers or your parents. So this can be viewed at this YouTube clip that I've put here. I have added that to the bottom of the Show My Homework reference. Okay, and then just to help you with the word terminology, concentric circles means 2 or more circles with the same centre point. So a circle within inside a circle, if that makes sense. And you're going to watch the clip, and what I want you to think about is what is the clip showing us, and what is the easy way to tell the direction of the current and the magnetic field that is being created. So, what was the easy way? We've got the electric current, and we're not initiating that you should suggest that you should put your hand around the wire. However, there is this the right hand and left hand rule. So this is the right hand rule, and that shows that if you were to imaginarily put your hand around the wire, the thumb shows the direction of current, and the fingers curled round the wire would give you the direction, your fingernails being the arrows on the lines of magnetic field, would show you the direction of magnetic field. So applying the right hand rule. If you think of a wire like a dart, okay, the thumb shows the direction of the current. The fingers show the direction of the magnetic field. The current flowing through the wire shows that the dart is travelling. If the dart is coming towards you, you see the tip. If the dart is moving away from you, you see the feathers crossed. Using the right-hand rule for the flow of electricity, magnetic fields can be illustrated like this. Okay, the dot shows in the middle that the current is moving towards you, and the magnetic field arrow is to the right. Whereas when the current is travelling away from us, we use the crossed feathers, and then the magnetic field is moving to the left. So we can investigate this, okay, using, as I said, a piece of wire through a piece of card, and using a plotting compass. And the needle of the compass shows me the direction of the magnetic field, and the strength of the magnetic field can be tested by moving the compass either closer or further away from the wire. Okay, the weaker the magnetic field, the further away it is, the weaker the magnetic field. The closer it is, the stronger the magnetic field. A bit like when you've got a fridge magnet and you move it away from the fridge, there is a point where it's no longer compelled to attract to the fridge. So this time you're going to do this as a virtual experiment. So what I would like you to do is use this link that I've again added to the bottom here, and observe what happens as you increase the current. Okay, we're going to increase the current. So what we've got here on my first sheet of paper here is just jumbled up iron filings. And if we increase the current from 1 amp to 2 amps, then 3 amps, look what happens to both the iron filings and the plotting compass. Okay, and think about this. Does it prove the right-hand rule? Okay, and what happens if you switch the direction of the current? What happens to the magnetic field? Okay, so this is just a quick knowledge check. Pause the slide and check your understanding. So here they are in red. Okay, so using the right-hand rule, what does the thumb represent? It's always the direction of the current. Then what can you say about the strength of the magnetic field? When the magnet is placed nearer the wire, the magnetic field is stronger the closer the wire. Now again, this is really important because this is what I keep referring to as an and statement. Nearer, stronger. That's a comparative. That is the difference for a lot of you between a 3 and a 4 or a 6 and a 7, because if you're not making those comparatives, you aren't going to be getting those marks. So lastly, key points. The magnetic field around the wire is circle centred on the wire, concentric in the plane of perpendicular to the wire. Mouthful that. And the current increases the strength of the magnetic field, or greater the current, greater the magnetic field, or the stronger. Reversing the current reverses the direction of the magnetic field, and the right-hand rule can be used to show the direction of current and the magnetic field lines. Okay, great seeing you. There is a SAM learning task associated with this. Look forward to seeing you tomorrow.